Okay, well, happy St. Patrick's Day. Okay, so last time we talked about some more about affine connections, and where we ended up was we ended up with the notion of a geodesic. And so a geodesic, remember, is some curve that satisfies an equation like this. And we saw that in coordinates, this amounts to some differential equation that looks like so. Okay, and we looked at a very elementary example, namely the plane R2 with its standard Euclidean Riemannian metric, and the geodesics for that thing, those being straight lines. Okay, and then I made some comments about the fact that, well, I guess we all know that straight lines minimize distance. So let me say a few things about that in general. Okay. Okay. Properties of geodesics on Riemannian manifolds. Okay, and so whenever I say, a Riemannian manifold, we know that it comes equipped with a specific affine connection, namely the Levi-Civita connection. Okay, so we're going to let MG be a Riemannian manifold. And so, of course, this means that M is a smooth manifold and G is a smooth Riemannian metric on M. Okay, and so we have the Levi-Civita connection that we denote like that. Okay, so based on what we have already done, what we know is that the geodesics for the Levi-Civita connection are the Euler-Lagrange equations for the kinetic energy. So we know that geodesics for the G are solutions to the Euler-Lagrange equations for the Lagrangian, which is the kinetic energy. Okay, so 1/2 mv squared, or 1/2 G of v comma v. Okay, because that was our starting point for seeing where affine connections come from in mechanics. Now we're going to look at a different Lagrangian, which is similar but not quite the same. Okay. All right. So if gamma, let's say from A to B, so defined on a compact interval, is a C1 curve. Okay, so it needs to be differentiable. So I don't often state the regularity assumptions here, but here I will, because we do need to differentiate it. So if gamma is a C1 curve, then the length of gamma is L G of gamma. Okay, so L for length, G, because we're going to see that the length depends on G. Okay, and what you do is you integrate from A to B, okay, and then you take G of gamma prime of T, gamma prime of T. Okay, now if we were to just take this and put a half out front, which and the half doesn't change anything. Half just makes it so that it's the kinetic energy and not 2 times the kinetic energy. But we're not going to do that. Instead, we're going to take the square root of that. Okay, so that's the length. So the length is related to the kinetic energy, it seems, but it's certainly not the same. And so what you want to do is you want to take 2 points on your manifold, and you want to minimize the length. Okay, so the first thing you will observe is that we don't really have to work with curves defined on AB. It suffices to work with curves defined on, it turns out, the interval 0, 1. And I'll explain to you why. So without loss of generality, we can assume that AB is equal to 0, 1. And this is because the length of gamma is independent of parameterization. So I'll explain what that means. Okay, and so what that means is you can parameterize the curve however you want. And so let's suppose we choose some parameterization, so that just means you choose some curve, and you want to reparameterize it. What would that mean? Well, what that means is that you're going to take a curve which is possibly defined on a different interval, and possibly goes along the manifold with different speeds, okay, than your original curve gamma. Okay, so gamma always has a speed gamma prime. Okay, so to see this, let's let tau from some other compact interval, CD into AB, be a reparameterization. And I'll explain to you what that means. Okay, so this means that tau is for our purposes, a C1 bijection. And tau prime, its derivative, is positive. Okay, and so we're just going to change the speed at which we go along the curve. Okay, that's the idea. Okay, all right, so now let's look at the reparameterized curve gamma. Okay, but not with its original parameterization, but reparameterized by tau. Okay, so LG of gamma composed with tau. Okay, so that's how you reparameterize. And then, so now the reparameterized curve is defined on CD instead of AB. Okay, and so it's the same formula. So let me call the parameter here S because I'll change it in a second. Okay. All right. So now what we're going to do, of course, is we're going to take the derivatives here with respect to S, okay, of the velocity, and we're going to use the chain rule on those, okay, gamma composed with tau. All right, so let me kind of skip a step here. So when you apply the chain rule, you're going to get gamma prime composed with tau prime, all right? So tau prime, we know, at every point S is going to be positive. Okay, so I'm going to get a tau prime here and a tau prime here. And those are therefore just going to, G is linear. So the tau prime squared is going to come out front. And then we're going to take the square root of it. And when you take the square root of the square of something that's positive, you get back to what you started with. And so what you get is this, is you get the integral, whoops, the integral from C to D, tau prime of S, and then in here you get G of gamma of, yeah, let me do this carefully. Okay, so it's going to be gamma prime at tau of S, okay, and then gamma prime at tau of S. Okay, so that's what you get from doing the chain rule. DS. Okay. Does it make sense? Okay. All right. So now what you do is, you notice that this is d tau by ds. Okay, so I have combining this with this. This is d tau by ds ds. That looks like it's crying for a change of variable, right? And so I'm going to define t to be tau of s. Okay, that's my change of variable. So the dt is exactly tau prime of s ds, right? And then, so you need to convert the limits from C to D to whatever the limits are for my new variable, which now is T, but of course that's AB. And so I get the original length. Okay, so the length of a curve does not depend on its parameterization. This is not true for the kinetic energy. Okay, and so let me write down exactly what I mean by that. I mean that the integral from C to D of the kinetic energy, which is 1/2 G of gamma composed with tau prime of S, gamma composed with tau prime of S ds is not equal to, generally, 1/2 integral from A to B, G of gamma prime of T, T. Okay, so this is something that's rather specific to length. And as we saw when we did this, the calculation which goes from here to here, the reason that this works out here is that you get, when you do the chain rule here, you get a tau prime and a tau prime, which gets squared, and then you take its square root. Okay, so that's the reason why that length function is independent of parameterization. Okay, and that's as it should be, right? If you want to talk about the length of a curve, it shouldn't matter how quickly you go along the curve. The length of the curve should be the length of the curve. Okay. All right, good. And so this is already a difference. There's an obvious similarity between this integral and this integral. Okay, but this is an important difference, is that one of them is parameterization dependent and the other one is not. Okay. All right. Okay. Anyway. So maybe let's just call that a distraction. Okay, so now what we want to do is we want to define the distance between 2 points. Say x1 and x2 in M, then the distance, okay, between x1 and x2 is, okay, so it's d sub g of x1 and x2. So this distance function depends on g, because we're going to define it using the length. Okay, and what it is it's the following thing. So it's the inf of the following collection of numbers, the length of all the curves, gamma, so that gamma is a C1 curve on the interval 0, 1 with values in M, okay, and gamma of 0 is x1 and gamma of 1 is x2. Okay, so that's how I define the distance between 2 points. And so I take all the curves which connect x1 and x2 and their lengths, and I take the infimum of those lengths. Okay. And so, for example, so let me sort of give you a question that you might ask: is this infimum always achieved? And the answer is no. And there's very simple examples to illustrate that. Okay, the infimum is not always achieved for a C1 curve gamma. Okay, so what do I mean by that? I mean that is there may not be gamma such that the distance between x1 and x2 is the length of this curve. Okay. All right, so let me just give a simple illustration of that. So if you just work in R2, okay, and what I'm going to do is I'm going to take away a point from R2. It doesn't matter what point you take, let's make it 0. Okay, so G is the Euclidean metric in R2 that we talked about last time, except it's not in R2, it's in R2 take away 0, but it makes no difference because the tangent spaces are still isomorphic to R2, and so the metric is still the same as the one we talked about last time. All right. All right, so maybe okay, so here's M, and we put a hole at 0. Okay, so my question then to you is, what are 2 points in M, the punctured plane, okay, where the distance between those 2 points is not achieved by a curve in the sense that that's true? What should those 2 points look like? Yeah, so for example, but it doesn't have to be. All it has to be is it has to be 2 points where the straight line that connects them goes through the origin, right? Because your curve then, to really achieve the minimum distance, the curve would actually have to go through the origin, but the origin's not in M, so it can't do that. So if you take any 2 points, so maybe let me draw 2 points for which it works. Oh, sorry. Okay. So out here, I have these 2 points, and there's no problem. There's a straight line that connects them. And so the distance between these 2 points is exactly the length of that curve. Okay. But if I take 2 points like this, okay, any curve is going to come along here, but you're going to have to go around the little hole there. Okay. And so the infimum of the length of all of those curves is going to be just that distance in the unpunctured plane, but there's no curve that achieves that minimum distance. Okay, so it's very easy to find examples, and this might not surprise you to know that this is a problem of completeness of the metric space M with this distance function. Okay, and so in 334, I guess you talked about a completeness of normed vector spaces. Well, normed vector spaces are particular examples of metric spaces where the metric is just determined by the norm. And here we have a metric, which is this thing DG, and it has many of the similar properties of a norm. And in particular, you can talk about Cauchy sequences, and the problem here is that this metric space is not complete. Okay? Removing the origin renders it not complete as a metric space. Okay, all right, good. So, but those things tend to be a little bit pathological. It's not that it's exotic; it's just that it doesn't normally happen. Normally, you don't remove points from a complete manifold to get an incomplete one. All right, so now let's make the following observation, general observation about geodesics. So if MG is a Riemannian manifold, and if X is some point in M, okay, and maybe let me call it X naught. Okay, so so what I'm going to do is I'm going to think about points in M that are close to X naught, so whose distance from X naught is small. Okay. Now, what I'm saying is that if X1 in M is such that DG X naught X1 is sufficiently small, okay, and I just mean that there exists some distance that if you're less than that distance, then the following thing holds. Then the distance between G, the G distance between X naught and X1 is LG of gamma for a geodesic gamma. Okay, so in other words, for points that are close, the distance between them is the length of some geodesic. Okay, that's what that statement says. And so let's maybe look at our little example up here. So let's take x naught to be maybe this point. Well, I know that I can't take x1 to be this point because that's too far away, and there's no geodesic for which the distance between that point and that point is the length of the geodesic. But I know as long as I choose points in there, that distance away, then it's always going to be the case that I can connect 2 points with a geodesic. Okay, that's sort of an illustration of that. Let me give a more interesting illustration. Because again, this one's silly a little bit because I've taken a nice example, which is R2, and I've made it not nice by removing a point. So let me take a nice example, which still illustrates that there's content to this theorem. Let's take M to be S2, the two-dimensional sphere in R3. Okay, so this is the set of points unit distance from the origin. Right, so the way you draw S3 usually is something like this. Okay, so let me pull out my circle drawing tool and see if I can move this thing. I don't know how you're supposed to move it. Oh, there we go. Okay. All right. Not that I moved it particularly well. All right. So the point is that center is supposed to be at the center of the circle. Sorry. Okay. And then around, let's call it the equator, you have a circle like so. Okay. So there's your S2. Okay. Now, S2 has a standard Riemannian metric on it. And what is that standard Riemannian metric? Okay, so the standard Riemannian metric on S2 is just the restriction of the Euclidean metric to the tangent spaces of S2. Okay, so S2 kind of has a whatever, a tangent space that maybe looks something like that. Okay, but the point is that that tangent space, because S2 sits inside R3, that tangent space is a subspace of the tangent space to X at R3. Okay, and so this one has its Euclidean metric that we talked about last time. Okay, because the tangent spaces are isomorphic to R3. We have the standard Euclidean metric here, which gives us an inner product here, which by restriction to tangent vectors there gives us an inner product on each of the tangent spaces to S2. Okay, so that's what you would call the standard Riemannian metric on S2. Okay, now this one has the feature that it's the length of a curve. Well, let me talk about distances instead. The distance between 2 points. Okay, so let's say I take 2 points on S2. Okay, so for simplicity, maybe let me take one of the points to be the North Pole. Okay, and let me choose another point which isn't that far away. Let's say here. Okay. how would you measure the distance between those 2 points? Just thinking about, you know, the Earth on which we all inhabit. How do you measure the distance between points on the surface of the Earth? Is there a name for the curves whose length you measure? Do you remember this? There's a name for, you know, the route that airplanes take when they fly. Great circles? Is that a term that's familiar to you? I'll tell you, geography. You don't learn geography anymore. That's okay, there's the internet. And so what's a great circle? A great circle means the following thing, is that you take a plane which contains these 2 points, okay? So it's some plane that I'll attempt to draw, like so. Okay, so these 2 points are in the plane, okay? And also, to determine a plane in R3, you need 3 points that are not linearly dependent. And it also passes through the origin of the of R3, and therefore the center of the sphere. Okay, so that's a plane, and it cuts the sphere through these 2 points, and it's going to cut it along a curve, which you can maybe draw like that. Okay, does that make sense? Did you know the thing I'm talking about at least, right? It's just the intersection of a great circle is the intersection of a plane that passes through the origin with the sphere. Okay, and so that cross section of the sphere is going to be some circle whose radius is 1, which is the radius of the sphere. Okay, and so the distance between 2 points is going to be the curve along a great circle. Okay, and so what this tells you then is that those great circle curves are the geodesics on S2. Okay, so by geography that you don't know, okay, the shortest distance between points on S2 is along a great circle. Okay, so great circle is the thing I just described. It's the intersection of a plane passing through the origin with the sphere. Okay. Okay. Now, so from this we can infer that great circles by the theorem. We can infer that great circles are geodesics. Well, we can't quite infer that. Let me explain to you why. Well, so certainly it's true that great circles are geodesics. What's not necessarily true is that geodesics are segments of great circles. Okay, so great circles are geodesics, and geodesics are segments. Okay, in exactly the sense that I drew here. That's a segment of a great circle. Okay, now, so let's take a look at an important part of the theorem here, which says that if x1 is a point which is sufficiently close to x0, then the distance between x0 and x1 is going to be the length of a geodesic that connects x1 and x0. Okay, all right, so now let's look at our circle example. All right, so what this says is that if I start at the North Pole, for points that are close to the North Pole, the distance between the North Pole and that point is going to be the length of this great circle segment that joins it. Okay, now what if my points get further and further away? Okay, so I'm going to go along this great circle, and you can shout when you tell me that the distance between the points along the curve ceases to be the length of the curve that I'm drawing. Okay, so I go along here. For short distances, I know that the distance from this point to this point is the length of that segment. Okay, so now I'm going to go along, and then at some point, it's going to stop being true, and you're supposed to shout, and you missed your chance. Okay, because it's the South Pole, obviously. Okay. All right, so when you pass through the South Pole, then the distance along that curve is obviously too large because, you know, if I want to get to a point out here, I should have gone the other way. Okay. And so that is one illustration of this reason why x1 has to be sufficiently close to x0 in order for this to be true. Okay. And there's a whole bunch more that's true here. Let me just talk about some other things. That for short distances, like I have here, the geodesic is unique. Okay, so the distance between these 2 points is determined by a unique geodesic. There's only one geodesic which connects those points, and that one minimizes the distance. Okay, now as my distance gets large, then the uniqueness of the geodesics that minimize distance is no longer true. So for example, when I come along here and I end up down at the South Pole, okay, from the North Pole to the South Pole, how many geodesics are there that connect the North Pole and the South Pole and which minimize the distance? 1, 2, 5, infinitely many, right? Because I can go in any direction from the North Pole, right? And I will still get to the South Pole, and the distance is going to be independent of the original direction that I chose. And so you can take any geodesic, or great circle, which starts at the North Pole and ends at the South Pole, and that one will be a geodesic that minimizes the distance between the North Pole and the South Pole. And there's infinitely many of those. And so there's this two things going on at the same time. And one is that the uniqueness property of the geodesics that minimize the distance is violated, okay? And also violated is the fact that when I go through these points, the distance stops being minimized, okay? So, and so for the North Pole, the South Pole seems to be kind of a special point. And it's what's called, in Riemannian geometry, a conjugate point. Okay. All right. So there's all kinds of interesting geometry there. And I just kind of wanted to give you a little flavor of it. Okay. All right, good. So that's one way of thinking about what geodesics are. And geodesics are associated with affine connections. And so that's one of the useful things that you can do with affine connections is you can use them to talk about distance on a general manifold with a Riemannian metric. Okay. Here's another way of thinking about what an affine connection gives you. Is that affine connections give you a device for talking about acceleration as a vector field along a curve. Okay, so from your homework, you remember that you showed that the acceleration q double dot does not satisfy the proper transformation properties to be to give you tangent vectors along the curve. Okay, so if you're going to talk about acceleration as being a vector field along your curve, its definition is not going to be q double dot. okay, because that's not a vector field along a curve. Okay, instead, so thus this thing so it does not define acceleration along the curve. Okay, but your feeling is that this does achieve that. Okay. Okay, and the reason, well, you know, just sort of stupidly, is that it has double dots in it. So I was using Q, so let me continue to use Q. Okay, and like I said, you know, it has a double dot, so it seems like it might be acceleration. Okay. So let me give you a very simple example that I won't work out all the details for, because Henry will look at this example in the tutorial this afternoon. Okay. And so example. Okay, so let's consider a curve, gamma, which maps t to the point cos t, sine t in R2. Okay, so I'm just talking about now a curve in R2. Okay, so it's, you know, we know what that curve looks like. Okay, so the curve outlines a circle. I go around a circle like this. Okay. And so obviously I've written the curve in Cartesian coordinates. Okay. All right. Now, if you write the same curve in polar coordinates, okay, it's, well, what's R along that curve? Well, R along that curve is 1, and theta along that curve is t. And so that same curve in polar coordinates looks like t goes to 1t. Okay, so this is the local representative of the curve in Cartesian coordinates, and this is the local representative of the curve in polar coordinates. Okay, so now let's calculate the velocity and the acceleration along that curve. Okay, in Cartesian coordinates, okay, velocity is, okay, so we just, you know, this is x of t and y of t, so we just go x dot of t d by dx plus y dot of t d by dy. So that's minus sine t d by dx plus cos t d by dy. Okay, and acceleration. Okay, so now I'm going to define the naive acceleration, which is just q double dot. Okay, so I'm just going to, you know, differentiate x of t twice and y of t twice, and so I get minus cos t d by dx minus sine t d by dy. Okay. So that's the naive, acceleration that we somehow feel like there should be something wrong with, and we'll see exactly that there is. Okay. And then the other thing that we can talk about is we can talk about this as being the acceleration. So this is kind of our proposed acceleration. So let's calculate that one as well. Okay. So I want nabla gamma prime, gamma prime. Okay. And so we calculated the Christoffel symbols. Well, we didn't calculate them. We saw that they were 0 for the standard metric on R2 last time. And so the this thing is exactly just the naive acceleration in these coordinates. Okay, so it's cos t d by dx minus sine t d by dy. Okay, now let's do the polar coordinate calculations. Okay, so velocity. All right, so so it's r of t theta of t. So the velocity is r dot d by dr plus theta dot d by d theta. So that's just 0 d by dr plus 1 d by d theta. Right, that makes perfect sense. I'm just moving with speed 1 in the theta direction. Okay, acceleration. All right, and so again, this means the naive acceleration, just the double dot acceleration. And so I take these now and I differentiate. I go r double dot of t, theta double dot of t, but that's 0 now. Okay, and so I draw your attention to, whoops, this. Okay, those things don't agree, right? Okay, but let's look at the acceleration defined by the affine connection. Right, so now this is the part of the calculation that I'm not going to work out and that Henry's going to work out this afternoon, because this one depends on the Christoffel symbols for the Euclidean Riemannian metric in polar coordinates. Okay, so that's what Henry's going to work out. And it turns out that what you get when you work that out is you get -1 d by dr. Okay, so there's a Christoffel symbol which shows up there. Okay, so now let me look at these quantities. Sorry, I'll be one more minute. I'm sorry. Okay, so let's look at these quantities depicted on our picture up here. Okay, so the position is fine. That's obviously independent of coordinates. It just gives me the position along the curve. Okay, so there's no problem with the consistency of the curve along the curve, obviously. Okay, same as velocity. Velocity makes sense. The velocity is a tangent vector, which looks like that. And it looks like that in both Cartesian coordinates and polar coordinates. Okay, but the acceleration, the naive acceleration in Cartesian coordinates, the naive acceleration is blue, and it points right directly in towards the center of the circle, right? So you know this from physics. As you go around a circle with uniform speed, the acceleration points to the center of the circle. Okay, and that's what this formula is telling us, and it's also what this formula is telling us. Because as we see here, when we represent the naive acceleration in polar coordinates, the naive acceleration is actually 0, just the second derivatives of these. Okay, and so this is the naive acceleration in Cartesian coordinates, but not in polar coordinates. But in polar coordinates and Cartesian coordinates, both of these things are nabla gamma prime, gamma prime. Okay, and so this thing is the thing that measures the acceleration that you expect as you go around this curve independently of any set of coordinates. Okay, and that seems like a good thing. All right. All right. So the punchline is affine connections allow you to define acceleration in a natural way. Okay, good. So we'll carry on next time.